Good afternoon. How is everybody today? I'm going to try to not put you to sleep with what we're talking about here today. Again, as Jeff said, my name is John Messick. I work for Nobles MSD, Mission Solutions for Defense. And I've been involved with machinery control systems for 30 years, since 1997. Working for Jeff part of that time, implementing machinery controls for propulsion, electrical distribution, damage control, you name the system. As we all know, ship systems for the U.S. Navy and cruise liners are like small cities. They have as many life support and other systems on board them as a small city does, which all require some sort of machinery control capability. So what I want to do is go into a discussion about ship control systems, network architecture, communication protocols, and message authentication options. See if I can operate this thing. So here's the agenda. We're going to get right to it. I'll just let you read that for a second. I don't need to read it with you to let you know what exactly it is I'm going to be talking about. And while you're reading that, I'm going to ask a question of you. And that is, what do you think the 2020 World Economic Forum's Global Report, I've got to read this a little bit, Global Report Risk Report said was the fifth highest risk? Does anyone know what that might be? Cybersecurity. So again, let me repeat that because the World Economic Forum's Global Report on Risk said that the fifth highest risk in 2020 was cybersecurity. That's kind of an important goal for us now, as it wasn't before. How many of us in here are ship machinery controls engineers? Anybody? Several of us associated with the idea of it? So there's a fundamental difference with ship machinery control systems that is different from IT systems. Ship machinery control systems are what are referred to as OT systems, operational technology, as opposed to your phone, your desktop computer, your apps that are IT systems, information technology. Two very different and distinct things, and they have two very different and distinct priorities, which drives the reasoning behind why encryption and message authentication has lagged behind in things like shipboard machinery control systems. So when we talk about cyber attacks, and now I've identified the fact that someone said that it was the fifth highest risk possible in the next coming years, me as a machinery controls engineer, I feel like, well, okay, I hear the risk, but is there really a vulnerability? Has there been really a threat? And what I found during my research, I looked that up, and I found that the U.S. Coast Guard actually published a few bulletins on that very subject. They published a bulletin about an incident of a deep draft vessel. Shipboard network was compromised. They also published another alert that said that malicious software was specifically designed to disrupt the shipboard computer system. So there you have two examples where cybersecurity isn't just a buzzword. Cybersecurity actually impacted what we do. Anyone seen the movie Speed 2? American movie? Speed 2 Cruise Control. Speed 2 Cruise Control is a fun movie for 10 minutes. 10 minutes, I say, because the villain in that movie is an actor, Willem Dafoe, and he self-describes himself in the movie as a machinery controls engineer for the cruise liner. And what he does is, he's funny because what he's able to do, he takes his laptop, as some of us have as a machinery controls engineer. It has the HMI software on it. He knows where the data points are to connect into the network. He goes into a stateroom where he knows the fiber cables are above his room. And they show this in the movie. He connects up the fiber cables to a hub. He connects his laptop to that hub. He starts to spoof out the damage control system, eventually locks up the engine and causes it to overload, and then eventually takes over the navigation system, causes the cruise liner to crash into the pier. That's the spoiler alert, but that's the gist of it. But 10 minutes of it is fun because he calls himself a ship machinery controls engineer. So what is he? He's a great example, a great illustration of a trusted agent insider threat. That's who he is. He has the software at his disposal, he has the knowledge behind it, and he has the capability to cause real harm. So what are we saying here? Fiction from 1997 has become true threat today. So what are the guiding factors we do as design engineers? Well, we have our priorities, we have our requirements, and then we have our design. And what drives that is standards in some cases. What are some of the standards that talk about encryption and message authentication? One of them is the National Institute of Standards Technology, NIST 800 TAC 82, that talks, it's titled Guide to Industrial Control Systems. And in there's some discussion about encryption. One of the fundamental problems with encryption with industrial controls is, one, they don't have the horsepower that an information system has. Their processors are much more limited. It's mostly because of real estate for that processor. It needs to be small. Being small, it can't handle the heat that's addressed with, I'll say, the horsepower associated with the larger processors like you would see on a desktop machine. Amazingly, your cell phones have it, but we can't seem to figure out how to do it with industrial controls. So what NIST also talks about is the issue of not only is the heat a problem, but what's more of a problem is the latency. Some of our industrial control systems, they respond far more fast than your phone. And this might be the answer why your phone can do it and industrial controls can't. Because your phone, as you're sitting here right now, you might be looking at your text messages, you might be looking at your emails, or even browsing the internet. And what's acceptable to you is the hourglass, waiting for that data to come in. It's not acceptable for machinery controls, particularly on shipboard operations. Imagine for a second if that hourglass affected the response time of a variable speed drive or even a motor responding to bad storms in the waters, high tides, or as simple as a toilet flushing on the ship. You need to respond to the pressure change very, very quickly. So again, the discussion of the need for cybersecurity is job one in trying to make sure that we put encryption into the process. We put encryption design into the process. In order to decide on the options, there's three things involved here: the network topology, the communication protocols, and then how do we get the encryption on those? Because legacy systems right now currently don't have it. Those systems are dictated by either the vendor choice or the network topology. So what we see again is this challenge that IT did it a long time ago. IT did it because their number one priority is confidentiality. Second to that is integrity, and lastly is availability. But what we find on the OT side, and this is taken out of an ISA standard, by the way, availability is job one, integrity is second, and lastly is confidentiality, which is where the encryption priorities sort of lie at the moment. What we also see here is on this particular graph, what's missing is safety. IT systems don't really have a need for safety. They have a need for confidentiality. They have a need for protecting that data from theft. But here on the OT side, the shipboard operational control system side, we have a very need for safety. And so what's happening is with cybersecurity, the threat is now involved with safety. The criminals aren't just involved with financial gain. They're involved in danger. They're involved in affecting safety. So we need to put the encryption process, the philosophy and need of encryption at the availability level as well, and the safety. So my discussion talks a little bit about networks, the network topologies, two basic industrial network topologies that were all our favorites, ring topologies and star topologies. Again, they're dictated by the vendor you choose, they're dictated by the communication protocol you pick, and those two decisions are going to derive what possibilities exist for your message authentication. Because with the ring topology, you might need a DNS server for your certificates and your digital signature management. Certainly your certificate management is going to be a part of the DNS server as well. So with that being said, nowadays, by the way, rings are much more reliable than they were in the past. As a matter of fact, I think they're more reliable than the star configuration because now you have a two-way directional ring. So you need more than one break in order for the ring to break. Whereas with the star topology, we used to be acceptable because if you got a break, you only lost one device on the network. But in the ring topology now, you need two breaks. You need two faults in order to lose anything at all. So getting to that point, there's another struggle with implementing in message authentication, and that is redundancy, availability. There seems to be the vendors, they took a path, and they took a path for either they wanted you to have a secure network or they wanted you to have a redundant network. A lot of times when you pick your vendor, you look at what their device options are, you're going to struggle with something, for example, redundant processors and the ability to use some of their canned message authentication capabilities. So here are some of the more popular communication protocols, and I can tell you that none of them, not one of them, has message authentication as part of its design. That's fundamentally the problem. So what the vendors are doing that design these systems, and some of them are 30, 40 years old, where again, the air gap was the acceptable break for security. It's no longer the case with our insider threat, remember, Mr. Willem Dafoe. So each one of these protocols, none is any better than the other in my opinion. They're really dictated by what vendor you pick, by what hardware you select, and what network topology you want to go with. But each one of them has its own challenges with implementing message authentication. So where do we want message authentication? We want message authentication between our operator consoles. We want message authentication between our operator console and our control processor. We want it between our processors, we want it between our I/O, and we want it to our Internet of Things devices, which are becoming more and more common. And that is these smart, autonomous devices that sit on our shipboard network that do a very specific task, and yet our higher-level machinery ship system wants to know what that device is doing. Again, very little message authentication occurs in these kinds of systems as of right now. So what are some of the possibilities currently, right now? If you were to talk to a vendor, ask a sales guy what he has available for message authentication, these are some of the possibilities. Something called OPC-UA, Open Platform Communication Unified Architecture, something called Transport Layer Security, which is an IT sort of a solution as well. And with the TLS solution, there's very strict and very difficult challenges for making that work with industrial control systems and shipboard platforms. Another possibility is a virtual private network. That's a very complex and expensive solution. It's typically used for peer-to-peer for remote access, which during my research, by the way, in writing this paper, I learned that one outcome of the pandemic was that what we were doing was we were connecting in our ship control systems remotely so that people on land could communicate with our ship systems for diagnostic purposes to help them keep running. So these particular kind of solutions, virtual private networks, were very important to making that happen. Another possible solution is what's called a bump in the wire. There are some companies out there that are building a gizmo, I'll call it, a microprocessor that you would put in front of the network communication device of your control system operating console in between each device, and it would actually mitigate the authentication for you and then pass that data along to the unauthenticated devices. That's also a very expensive possibility, but in terms of a solution for today's ships, there's two possible problems here. One, dealing with the ships that are on the water right now, and dealing with ships that we're putting on the water 2 or 3 years from now. And by the way, those ships that we're putting on the water 2 or 3 years ago were designed 2 years ago. So we need to have those solutions also implement from 2 years ago. So one more possible solution that's exciting to me is a solution that I'm investigating through Nobilis MSD, and that is I'm inspired by a thesis written by Dr. Ken Fisher, who is the cybersecurity lead at Naval Surface Warfare Center, Philadelphia. He wrote a thesis called Control System Data Integrity Using Variable Round Message Authentication Code with an Elliptic Curve Key Exchange Protocol. That's a lot to say, and there's a lot involved in that. And basically it breaks down to an existing cryptography algorithm with secure hash algorithms similar to your IT systems, a hash message authentication, because the trick here isn't encrypting the data. The trick is authenticating the data. It took me a little bit early on to understand the difference in those two concepts. What we want, we don't need to, I personally don't care as a controls engineer if someone sees my data. I care if they manipulate it. So what I want to do is encrypt it and authenticate it to make sure that the data coming to me, to my processors, is correct data. And that man-in-the-middle attack, Mr. Willem Dafoe, can't do what he wants to do. So, and lastly, elliptic curve Diffie-Hellman key exchange algorithm. So the way this concept works is every device has its own private key. There is a public key, and between the private and public key exchange, that creates the hash, which encrypts the data payload, along with some other data, like a timer, for example. And then each different device has to unencrypt that hash to validate that the payload is valid. One of the benefits to this solution is there's no impact on the topology. It's not driven by the topology. It is driven by the capabilities of the processor, which is, again, where NIST came in and said, whatever you do, you've got to make sure that your latency isn't a problem. This particular solution has had some very promising results. We've got it down to, for example, 7 milliseconds, I think, for a 400-byte packet. And with another key element to this is vendors of the hardware. And by the way, the next guy up will talk on this issue. He's going to tell you about how the challenge is to get these processors faster, the challenge to get these processors to be able to do this sort of encryption. Well, right now, what's going on in the industry is they've moved from 32-bit memory to 64-bit memory. That allows that complicated point math applications of that Diffie-Hellman key exchange and the hash authentication code to be done with much higher performance. The 64-bit memory processors are a huge step in the right direction for allowing message authentication, and in particular, this software solution. So conclusions, well, we have a need for cybersecurity. We know that we have a limitation between the network topology, the communication protocols, and what options we have for message authentication. And by the way, my white paper goes into more detail into these different message protocols and what possible message authentication capabilities you have with them. But I don't want to lose the audience with having those sort of detailed discussions. I want to expose you to it instead. So communication protocols discussed directly relate to the network topology. That's another piece of it. It's all about the design or redesign. You have to look at your network, you have to look at the communication protocols you currently have, which are probably 30 years old, and figure a way to make them more authenticated and secure. And again, don't worry much about stealing the data, worry about authenticating the data. So industrial automation vendors are currently actively developing new technologies for OT specific for IC. One of my objectives of the research I was doing was to do what I call due diligence with a trade study. What is out there now? What's available now? And get past the sales pitch. Can I actually implement what is available now? What are those struggles? If I pick a certain hardware, but I don't have the right network topology, I can't do it. If I pick the wrong communication protocol or I want redundancy, I can't do it. And lastly, what the hardware solutions to come, well, we're looking 5-10 years down the road to beat this problem, because the solution is, what the vendors are trying to do is get better, faster processors. And with that, I'm done.